look at some graph sketching. So we're going to review basically what you would have done previously with polynomials and rational functions. How do you graph these? So let's start with a polynomial. So the key thing to a polynomial is essentially we just need to get it into factored form. That will tell us our x-intercepts. And then we can also determine the y-intercept by just, well, in this case, looking at the end. When x is equal to 0, y-intercept is -1. But let's just get this factored first. So to factor this, we just need to use factor theorem. So I'm just going to actually call this f of x. And if we plug into f of 1, well, take a look at this. 1 minus 2 plus 2 minus 1 is equal to 0. So x minus 1 is a factor. Yeah, so factoring still plays an important role even in this calculus course. All right, so there's a number of ways you could get this factored based off x minus 1 being a factor. I'm just going to use synthetic division. So we're going to put the 1 there, 1, -2. Since it's x squared is missing, put a 0 there, 2, -1. And drop the 1. 1 times 1 is 1. And that's going to become -1, -1, and 0 is -1. 1 times -1 is -1. 2 and -1 is +1. 1 times 1 is 1, leaving us with 0 at the end there. And so then this tells us that y, or f of x, is going to be x minus 1, x, not cubed or squared, but cubed, minus x squared minus x plus 1. And you might think factor theorem again. Yeah, that would work. But we can actually do this a little bit more efficiently. If we take a look at the outsides, you have a 1 and a 1, so 1 times 1 is 1. And the insides, -1 and -1 is 1 as well. So that actually means we can use grouping, because we're looking at the outsides and the insides. Okay, so if we use grouping, x minus 1, factor out what you can, so x squared, x minus 1, minus, take out the negative, x minus 1. And so then you're left with x minus 1 times, well, another x minus 1. And then what's left over is x squared minus 1. And if we take a look at that, we can now further factor that x squared part. It's a difference of squares. So that's just going to become x minus 1, x plus 1. And all these factors that are the same, let's just combine them together. And we've got x plus 1 at the end. Okay, so we want to get these x-intercepts onto the graph. So x equals 1, x equals -1. And I'm also going to mention the order. So order 3, or multiplicity, you might say, and order 1. And that's going to tell us how the root looks like, what the behavior of the graph around that x-intercept is. So let's plot that down. So we have 1 and -1. Let's spread it out. We've got lots of space. 1, -1. Okay, so the other information we want to make use of is, well, f of x is quartic, or degree 4, which means it's even. 4 is an even number. And not only that, it has a positive lead coefficient. And so because of that, we also know that it's going to be starting off, it's going to end in quadrant 1, going up and away, but it also means that it's going to start in quadrant 2. So it's going to go from quadrant 2 to quadrant 1. Okay, so we've basically got all the information. The last thing is just the y-intercept, which is just, well, in the expanded form, it's just the end part. Because if you plug in 0, all of that's going to disappear, all those x's, and you're just going to get y equal to -1. So let's plot that down as well. There we have -1. And let's just basically connect this together in quadratic or quartic fashion. So using our end behavior and then using our orders. So the first root is order 1, so we're just going to basically go through it. We're going to go towards that y-intercept. And then as we approach the next root, make it look like kind of a cubic because it's order 3. So we have that little bend there. And up and away. And there we have it. That's just an example of graphing a polynomial. So again, get it factored, get those x-intercepts, use your y-intercept as well, and make sure you're taking into account the orders of those x-intercepts and just the overall behavior of the graph based off its degree and its lead coefficient. Okay, next, let's take a look at rationals. So these are trickier than polynomials. There's a little bit more going on. If we're looking at a rational, it's just a polynomial over a polynomial. So that's what we have here, is just a x to the n. It could keep going over some other polynomial. And essentially what matters is the degree of the polynomials in the numerator and the denominator. So if the degree in the numerator is smaller, so that's what this is saying, then what we know is that there is a horizontal asymptote. Not only that, if the numerator is smaller, it basically means the denominator is dominating the behavior. So you have some small number over a really large number, and something small divided by something really big, it's going to take you to 0. All right, if the two degrees are the same, so they're kind of balancing each other out. So in this case, you basically need to look at the lead coefficients. So A over B. In the last case, well, if the numerator is larger, it's dominating the behavior, so you're going to have some large number divided by something small. So no horizontal asymptote. There could theoretically be something like an oblique asymptote, but we won't look at that in this case. All right, so let's take a look at this first one. So when we're sketching this graph, we want to make use of intercepts. We also want to make use of asymptotes, and then also asymptote behavior. So I'll just write that down. Intercepts, asymptotes, and behavior. And if there's holes, yeah, make sure to take those into account as well. Okay, so that's basically kind of the key things we're going to be looking for. So let's start with our intercepts, why not? So our x-intercepts always come from the numerator, because if you set a fraction equal to 0, you just need the numerator to be 0. So 3x minus 2 equal to 0 implies that x is equal to 2/3. Okay, so that is our x-intercept. Our y-intercept, let's take a look at that. And if we take a look at the y-intercept, that's just plugging in 0, so it's just going to be g of 0, which is just going to be negative 2 over negative 1, which is just 2. So y is equal to 2. Okay, we've got our intercepts. Let's take a look at the asymptotes. So we have same degree over same degree. So because of that, our horizontal asymptote is going to be, well, just the lead coefficients. So in this case, the lead coefficients are 3 and 4. So it's just 3 over 4. And our vertical asymptote, we just have one. The vertical asymptote always comes from the denominator, because we're just checking when does this function potentially divide by 0. And that's what causes a vertical asymptote. In this case, you have 4x minus 1, which is going to lead to 1 over 4. All right, so let's plot down those asymptotes, and then we'll figure out the behavior of those asymptotes afterwards. But we'll just get down to the plot of the asymptotes first. So 1/4, we're just going to give ourselves some space here. Make sure to always label your asymptotes. And also, let's take a look at 3/4. So we'll do that a little higher up. It's not perfectly to scale. And also use a ruler. Pretend like you can see me using a ruler right now. That is not straight. Let me try that again. That was really bad. Okay, that's it's not great, but we'll make it work. Okay, so we have 3/4 and a quarter there. All right, so now let's figure out the behavior of those asymptotes, and then we can go ahead and really fill in this graph. So for figuring out the behavior of asymptotes, what I sometimes like to do is just make a number line. Actually, no, in this case, let's not do that. We'll just go straight to plugging in test values. So HA, behavior as in horizontal asymptote. So for the horizontal asymptote, let's see what it's like. So all we need to know is what's happening as you go to infinity, what's happening as you go to negative infinity. And all I'm going to do is test some large number. So I'm going to test 1,000 or a negative 1,000. And just plug it into your function and just see, are you actually above or below whatever the value of the horizontal asymptote is? So are we going to be bigger than 3/4 or smaller than 3/4? So I'm just going to quickly do a quick calculation and then we'll see what happens. Okay, so for our first one, we get 0.749. So g of x is approaching from below. So I'll write it as g of x approaches 3/4, but slightly smaller, so take away something from 3/4, so the negative sign. Let's try the next one out. And for the next one, we get 0.751. So a little bit bigger. So g of x approaches something from, well, the 3/4 from above, so a positive. All right, and the vertical asymptote behavior, again, just pick something near your vertical asymptote. So in this case, we're picking something around, well, x equal to 1/4. So as x approaches 1/4 from the left, so something smaller, and as x approaches 1/4 from the right, something bigger. All right, so let's test a value near that. Okay, so I've tested x equal to 0.249, that's slightly below 1/4, and we got 313.25. So that is going to tell us that g of x is going towards positive infinity. Let's try it again. All right, and if we test it out from above, as in slightly bigger, I did 0.251, you get negative 311.75. So it's going towards negative infinity. All right, let's put this all together and see what our graph looks like. So for our graph, we're going to plot down, first of all, our intercepts. So we'll make the graph purple. We will plot down x equal to 2/3, so that's, well, definitely bigger than 1/4. So I'll put it way over here. And then y is equal to 2. Well, that's definitely bigger than 3/4. Okay, the scale, okay, it's admittedly not that great, but let's get these other parts on there. So next, we want to make sure as we go towards positive infinity, the graph is going to approach from below. And towards negative infinity, it approaches from above. So something like that. And then the other things, and we can already kind of predict what it's going to be, like infinity towards the left and negative on the right. But let's just confirm that looking down here. Yeah, on the left, positive infinity. And on the right, negative infinity, like that. So there we have it. That is our first graph using those intercepts, asymptotes, checking the behavior. In this case, we had no holes. Let's go on to one that's got a little bit more to it, where we'll have to be, again, a little bit more careful. All right, so we've got the function x squared over x cubed plus x squared minus 2x. So we want to find the asymptotes and the intercepts. We want to check if the graph crosses any of the asymptotes. And we'll see how to do that and sketch the function. Okay, so before we get started, this is one where we want to just double check, can anything actually maybe cancel out? Can we simplify this before we begin? So always check to simplify your graphs or your functions if you can. So I can already see we can factor out an x in that numerator, or denominator, I should say. And, well, look at that. X and a 1 from the numerator is going to disappear. Not only that, if we check our denominator now, x squared plus x minus 2, well, that seems factorable to me. In fact, it's x plus 2, x minus 1. And so there we have it. That's much nicer to work with. So since we canceled out an x, let's make sure we just mention that we have a whole at x equal to 0. Not only that, let's find out the y value. And to find out the y value, just plug it into your simplified equation. So that's going to be 0 over, well, it really doesn't matter what's in the numerator at this point. 0 divided by, as long as it's not 0 in the numerator, 0 divided by some number is 0. So we've got a whole at 0, 0. Okay, so we'll make sure to include that when we graph our function. Now let's get on to the other parts like we did in the previous one. So let's start with those x-intercepts. So the x-intercepts, check your numerator. We have x equal to 0, but be careful. This is our whole. So since we had an x squared originally there, the 1 disappeared because it was a whole, but didn't make it fully disappear. So it still looks like it's an intercept, but it's not. So this is our whole. So no other, or no x-intercepts really then. Y-intercept will pretty much always happen unless you have your vertical asymptote on the axis itself. So for the y-intercept, plug in 0 for x. Well, and guess what? I just said pretty much always happens. But when we plug in 0, we get 0. But again, this is our whole. So we actually do not have a y-intercept in this case because we're passing through the origin essentially, which would be both an x and a y-intercept, but it's a whole at the origin itself. So let's focus in on those asymptotes. So for the horizontal asymptote, we look at the powers, the degrees. So we have a bigger degree in the denominator, which means the bottom is dominating. You're dividing by some large number. Something divided by a large number, we'll just go to 0. The vertical asymptote, well, in this case, asymptotes. Just look at those factors. We have x equal to 1, x equal to -2. All right, so when I'm dealing with something with a horizontal asymptote of 0, in terms of figuring out the vertical asymptote behavior, I always just like to do a quick number line just to figure out when is the graph positive and negative. And that will then right away tell us whether we're going to positive infinity or negative infinity, because it will basically be above or below the asymptote. Okay, so on here, on the number line, basically you want to check when is it positive and negative. So check your asymptotes and any intercepts and wholes. So what we're going to do is we're going to check 0. That was the whole that looked like an x-intercept. 1. Oh, and I should do things in order. So start with -2, 0, and then 1. And we're just going to do some test values. So I'm just writing out what values I'm kind of putting in. I'm not actually going to do calculations, but we're just going to check for the signs. So going to our function, we have, I'll just write it again, x over x plus 2, x minus 1. So when I'm testing out these values, all I'm looking at is the sign. So if I'm plugging in -3, we have a negative on top over, well, -3 plus 2 is negative, times -3 minus 1 is negative. 3 negatives together leaves the answer as negative. And I'll just continue doing that. So -1 means you have a negative on the top. -1 plus 2 is now positive. -1 minus 1 is negative still. So 2 negatives give you a positive answer. And we'll just keep going forward. So a positive number at 0.5 is going to make the numerator positive. 0.5 plus 2, well, is definitely positive as well. 0.5 minus 1 is still negative. So 1 negative now leaves the answer as negative. And the last part, if you pick some big number, bigger than all those factors, well, all the parts are going to be positive, which is going to make the answer positive. All right, so this actually tells us our asymptote behavior. So we're looking at, let's say, the asymptote at -2. On the left side, we know we're negative, so the asymptote behavior must be approaching, well, it must be approaching negative infinity on the left. So on the right, it's positive, so it must be approaching positive infinity. We still want to figure out, well, and even actually, this tells us our horizontal asymptote too. Since it's 0, since we're on the right of 1, as we go towards positive infinity, essentially, we're going to be positive. So through this tells us all asymptote behavior. So we don't have to do all these test values, but this is only able to work if our asymptote is exactly y equal to 0 for the horizontal asymptote. That is key, because then we can simply just look at positive versus negative, which tells you above or below. All right, so let's finish things off by drawing ourselves a diagram. Actually, no, there's one last thing to check. In the question, it asks if we have any crossing of the asymptote. All right, so yeah, I did kind of ignore that. It's because we've already kind of secretly done it. If you want to figure out a graph crosses an asymptote, all you need to do is set it equal to your HA, as in your horizontal asymptote. But what was our horizontal asymptote? Our horizontal asymptote was 0. And if we're setting our equation, our function equal to 0, well, that is actually what trying to figure out, in this case, the x-intercepts were. Because the x-intercept is when it crosses y equal to 0. So in this case, same as x-intercepts. However, if you had a different value for a horizontal asymptote, you would just set your equation equal to that value of the asymptote. Okay, so now let's actually go ahead and get drawn. So we'll start with our asymptotes. That's what I always like to start with. We'll try to keep things roughly to scale. So we'll call this 1. Again, label your asymptotes. Use ruler as well too. And y equal to 0, I'm going to draw it just slightly above, just so that you can actually see it. But of course, it would be directly on that x-axis. Okay. There's y equal to 0. Now, let's plot any intercepts we have. Well, I guess we just have the whole. So we'll still plot the whole. So that's at 0, 0. And then let's plot the rest of the graph. So to the left of -2, our graph is negative. So that means we're approaching this horizontal asymptote from below and going towards negative infinity. Next, on the other side, we're positive. I should have put this label elsewhere. And then we're going to approach that hole. And then we're going to go towards a negatives afterwards. And again, we're approaching these asymptotes. So make sure you draw it actually getting closer to the asymptote as you continue along. Okay, I'll label it down here. And lastly, the last section after 1 is positive. So we're going to approach positive infinity and then approach that graph or that horizontal asymptote from above. And there we go. So there we have it, a graph of that more complicated rational function where in fact we are crossing, well, kind of crossing, we have a hole at that horizontal asymptote. All right, and that's a review of rational and polynomial functions.